Okay, welcome to lesson 9.2. This whole chapter is about combining functions, and in our first lesson 9.2 we're going to look at the sums or the differences of two functions together. So we're looking at all of our parent functions here. F and G could be any one of those parent functions from grade 11 or from grade 12, and we're going to today look at adding those two functions together or subtracting those two functions. So some of the notation that we're going to see here is if we have in brackets f plus g of x, that's the same as f at x plus g at x. So this is just kind of a shorthand. And then again, the shorthand for subtraction, f minus g of x, is the same as f at x minus g at x. Now, we can only add or subtract functions if the x values exist in both of the original functions. So this means that our domains have to overlap. And we're going to look at that more throughout this lesson. The x values, when I add or subtract the functions, the x values are actually remaining the same. I match up those x values and then I just add or subtract the y values. So we'll take a look at a numeric example here first. So here f is just this function with a list of 4 points. So it's just a scatter plot on the graph. And then g is another function, and this function has 5 points. So in order to combine these functions, the first thing that I'm going to be thinking about is, well, my domain has to match. And it's where that domain matches up that I'm going to find my new function. And so that means that I'm only looking at the x values that match. So let's see if we can find some matching x values. So see here that f at x has an x value of -1 in the first point. And I can see that g at x also has a point at -1. Now, f at x has an x value of 1, and g at x also has an x value of 1. So we're going to use both of those. And then I also see another match. Here I see that there's an x value of 2 in f and an x value of 2 in g. So that means that this point here in f with an x value of 5 has no match in g. So that point is not going to end up, or that x value will not end up in our new function. Only these 3 x values will end up in our new function. So for our first example, we're going to be looking at adding f plus g. And so we'll say that f plus g is equal to, I'm just mimicking, notice the notation that they used up here. They said f is equal to the set of, and then they listed the points. So I've got f plus g is equal to the set of, and then I'm going to list the points. Now the first point will have that x value, and the x values were already in increasing order, so they're going to be in increasing order for me. -1 first, and now I have to figure out the y value. Now I'm going to figure out the y value by adding the two original y values. So 2 plus -3, that gives me -1. And then my second point is going to have that x value of 1 matched in both of the functions. And again, to come up with my y value, I'm just adding the two original y values. So 4 plus -2 is 2. And then for our last point, the x value that matches is 2. Notice the x values aren't changing. It's only the y values I'm adding. So 3 plus -3 is 0. And that's the end of that set. So f plus g will only have 3 points. In part B, we're going to look at f minus g. So again, I'm going to set this f minus g is equal to the set of, and this set is also going to have 3 points. It's only going to use the points where the x values matched in the two original functions. But this time we're going to take the f value and subtract the g value. So starting with the f number, the y number was 2, and I'm subtracting -3, so adding 3. So for the x value of -1, I get a y value of 5. And then moving on, my second x value that matched was 1. I'm not changing it. I'm just going to subtract the y values. So again, starting with 4, because I'm starting with f, starting with 4, I'm subtracting -2, so that ends up being +2, and I get 6. And then for our x value of 2, again, subtracting the y values, I start with 3 and I'm subtracting -3. So that'll give me a +6 as well. All right, so now some bigger questions. Is g plus f, if I did g plus f instead, would it be the same as f plus g? And hopefully we can see that yes, it would. And that's because the order of addition doesn't matter, right? Like if I do 2 plus negative 3, that's the same as negative 3 plus 2. I'm going to get the same answer, negative 1, no matter what. And then you can think about all different kinds of functions. For instance, when I look down here at negative 2, if I was looking at f plus g here, 0.5x plus cos x, that's going to be the same as cos x plus 0.5x. The order doesn't matter when I'm doing addition. So this is actually always true, that g plus f is equal to f plus g. Not just for this particular example. All right, now what about g minus f? Would that be the same as the answer that I got here for f minus g? So again, they're asking, does the order matter? Here we started with looking at the f number and subtracting the g number. What if I went the other way around? So for my first point, I did 2 minus negative 3. Would that be the same as going the other way around, negative 3 minus 2? And so here I would end up with 5 on the left and negative 5 on the right. So these are not equal to each other. So g minus f would not be the same as f minus g. Now, is that ever going to be true? So we know it's not always true, for sure not always true. But is it sometimes true? Well, yeah, it would depend on the function that you have. Usually when you get some simpler functions, it would work out that it's going to, it would work. I'm trying to think of an example off the top of my head, and I can't right now, but it is sometimes true. All right, in our next example, we're going to combine functions graphically. Now, you might find it helpful to make a table of values whenever you're doing the different graphs, but you don't have to. I'm going to show you that strategy in this example, and then I'm going to talk about what's another strategy that I could use. So in this example here, I've got f at x is 0.5x, so it's just a line with a slope of 1/2. And then here g at x is cos x. So that's actually a more complicated function. So I'm probably going to actually start focusing there, and the line is easy to find points on. My job is to graph those two functions, and then in part B, I'm going to graph the subtraction of those two functions. So that's some sort of weird function that I don't know anything about. And then finally in part C, I'll state the equation. So to get started on the graphing, I'm going to make a table, and I'm going to use the same x values because I'm looking for that overlap. Now here, when I'm thinking about combining these two graphically, I'm remembering that for a line, the domain is x belongs to the set of real numbers, and that for a cos graph, the domain is also x belongs to the set of real numbers. So these actually overlap everywhere, and so the domain of my new function is also going to be x belongs to the set of real numbers. So when I choose my x values, I'm actually going to start by thinking about the cosine graph. And I know that the cosine graph has key points at 0, pi by 2, pi, 3 pi by 2, and yes, we still live in radians. We no longer live in degrees in this course, right? We're always using radians. And then I'm going to figure out, well, what is the y value for the f function, so 0.5x? And then I'm going to figure out, well, what's the y value for the cos function, that's my g at x. And then finally in part B, we'll add my f minus g function. I'm going to actually do the cos graph first because it's the easiest one. The cos graph at 0 has a height of 1, and then it goes to 0, then it dips down to a minimum, and back to 0, and then back up to a max. It's nice and fresh in our heads because we did our trig unit recently. Now I need to figure out what is half of all of these x values. So because I am graphing these points, I am going to use my calculator here and change these pi by whatevers into decimal numbers. So the first one, 0 times a half is 0. And then I'm going to do pi divided by 2 on my calculator, and that gives me 1.57. But then I'm going to take half of that to put it on the line. So 0.79. And that's approximately, that is rounded. And then I'm going to take the number pi, and again, I'm plugging it in for my x value. So half of pi, that's 1.57. And again, that's approximate. That's my wavy equal sign. It's hard to do here. Now, let's see, I'll do a better job here. Wavy. It's approximately. So this time I'm going to do 3 times pi divided by 2, but then I'm also going to multiply by a half here, and that comes out to about 2.36. And then the last one, again, 2 times pi, but divided, or times a half, that's actually just pi, so it's 3.14. All right, so this is going to help me graph my two functions. So again, my cos graph, I think, is where I'm going to start. So I'm going to be thinking about using a scale of pi's. And that means that my pi by 2's are also going to be important. So halfway points are also going to be important. And then just the same scale backwards. There's my x-axis, and now for my y-axis, I can see here that for my y's, I need to see up to pi, and I'm going to tell you that for f minus g, that's also going to work. If you weren't sure how high these values were going to work out, then I would just fill in this column, and you're doing the f number minus the g number before you decide on your scale. So I'm just going to go up 1, 2, 3, and down 1, 2, 3. All right, so now we're going to plot some points. Again, I'm going to start with the coast graph. Just putting in my key points first, and then I'm going to try and connect the dots. Okay, so there's my f at x. I'm going to label it. And just for some color difference here, I'm going to use green for my line. So at 0, we're at 0, and then we're just going half the height of each one. So 0.79, it's going to be about here, and then half of pi, so 1.57, and then half of 3 pi by 2 is going to be about 2.36. And these guys should be ending up in a line here. Hopefully we're comforted by that. And then I'm just going to grab my line tool or my ruler, and we'll drag that out. Okay, so now we've got our line, we've got our coast graph. We just need to come up with the subtraction now. So the subtraction, I'm just going to put f minus g up here, and then in part C, we'll actually come up with the equation for f minus g. Now, f minus g says take the f value, remember f is the first number here, 0, and subtract the g value. So I'm just subtracting these values. I got 1.57, and I'm subtracting -1, so adding 1. And then 2.36, subtracting 0. 3.14, subtracting 1. And I've got my new values. So I'm going to plot those values. I'm going to use red so it kind of stands out here on my graph. So at 0, I'm at a height of -1. And then, so now I'm focusing on this x column here and the y values at the very end of the table. So at pi by 2 for my x, I'm going up to a height of 0.79. And then when I move over to pi for my x, I'm going up to 2.57. And then 3 pi by 2 is here for my x, so I'm going up to 2.36. And then 2 pi, I'm going up to a height of 2.14. Okay, and this pattern will repeat on the other side here. And the other way that you can come up with these points, instead of coming up with a table of values, the other trick to find f minus g is just find the points in the original graphs that are on top of each other and subtract the y values. Now being careful, of course, about my order. So I know that here it's f minus g, so it's green minus black. So if I wanted to say slide over to -pi by 2, I'm going to take the green value and subtract the black value for the y's. And so the y value of the black is 0, so the green value is actually not going to change, and I'm going to see my point end up right there. And then sliding over again to pi, I'm finding the points that are on top of each other, the y values that are on top of each other, and I'm taking the green height and I'm subtracting 1 from it. So I'm going to end up about here on my graph. And then sliding over to -3 pi by 2, again taking the green graph and subtracting the value of the black. Well, the black is 0, so the green one's not going to move. I'm going to end up right here. And so we can continue our graph this way. And when I connect the dots here, what I actually get is like kind of like a stretched out cosine curve. So I'm connecting in a smooth curve. And there it is. And you can double check my work on Desmos. We could figure out the equation to type in. And again, if this was a test, you wouldn't be able to check it on Desmos, but you could take a look at that, this shape of this graph. You can see the influence of the line, and you can see the influence of the coast curve, right? There's a waviness to it, but it's also going up on the right. For the equation here, it's just going to be the equation of f at x. So again, if you're, just because we are starting out here, f minus g at x is the same as f at x minus g at x. So I'm taking the f at x equation, 0.5x, and I'm subtracting the cosine equation, cos of x. Now here, there's nothing I can do to simplify these two together, and so that is as simple as I can get. That's the equation of this curve. All right, moving on to our next section. We're going to talk about combining functions algebraically, which we just did there at the end of the last example. It says when adding or subtracting, many functions will only simplify when combined with a function of a similar type. Polynomial and rational function combinations will definitely simplify when we're adding and subtracting, and sometimes they'll simplify with some of these other things. But logarithmic, exponential, trigonometric, radical, that's our roots, and absolute value functions, they typically don't add or subtract nicely with others, and we kind of get stuck. So that's just a note on simplification. I'm going to try and simplify these guys together for you just so you have a couple more examples. Now, domain and range. When we look at the domain, for x to be in the domain of f plus g or f minus g, it must be in both of the original domains. So we're looking for the overlap. For range, there are no set rules. Usually what we do is we look at a sketch and we kind of check what might be a suspicious value by plugging it into the equation. In this question here, we're only going to focus on domain for this lesson. So we're going to come up with a domain of f minus g for each of these two pairs. Now, again, I just want you to see some practice with algebra. So I am going to write down the algebra for f minus g of x. And again, that means f at x minus, g at x. So I've got 3 root x minus 4 minus 1 over x plus 1. And this I can simplify a little bit. Again, whenever I see my rational, I'm going to double check that I can. I can simplify this by coming up with a common denominator. And here my common denominator would be x plus 1. And then I would need to multiply this numerator by x plus 1 to combine these two things. So then my overall equation would be 3 times x plus 1 times the root, all minus 1. And then all of that would go over x plus 1. All right, now domain. So to come up with the domain, what I think about is, first of all, what is the domain of the original functions? So for the domain of f, I'm thinking about my parent function. I can remember that my parent function for a root looks like this. And I can see that there's been a vertical stretch. That's not going to change my domain. But there has been this shift of -4. So remember, when it says -4 and it's under the root, that means that it's a horizontal shift and -4, so it's going to go the opposite direction. So I'm going to see the graph actually over here and shooting this way now. So that tells me that my domain is x belongs to the set of real numbers, such that x is always going to be greater than or equal to 4. And next I'm going to take a look at the domain of g. And again, hopefully we're remembering this, that when I have 1 over x plus 1, you could be thinking about this as a transformation of your 1 over x graph from grade 11, or you could be thinking about your rational function graphs that we just took a look at in chapter 5 this year. This guy here is going to have a vertical asymptote at -1, and then it's going to have those 2 swooping sections like this. Right? That's what that graph looks like. And what that means for the domain then is x can be anything except x cannot equal -1. So I've got my 2 original domains. Now I can come up with the domain of the combination f minus g. So again, x belongs to the set of real numbers. Now we have to come up with the restriction. And it is the combination of the two things. So this thing says x has to be everything greater than 4, and we also want to combine that with cannot equal -1. Now, so normally what we would write, normally what you would see people write is x is greater than or equal to 4, comma, x cannot equal -1. But in this case, I actually don't have to write both of them, because when I say x is greater than 4, that implies that x cannot be negative. So x cannot be -1. So I don't have to write this because I'm just repeating myself. So I'm going to get rid of that and just close up my set here. And I've actually included both of the originals in this statement. And I'm going to just make a note of that so you don't I didn't forget it, I didn't ignore it. This already implies. So it's hidden in there. Okay, next example we're going to take a look at, we've got a logarithmic graph and an absolute value function. So again, I can take a look at the equation for this. They are still asking me to take a look at f minus g. So f minus g at x, remember that's f at x minus g at x. So log. And you can play around with these on Desmos just for fun, just to see kind of like, what are these weirdos, what are they going to turn into? And you should see an influence of both of the different types of graphs together. This one here, I can't simplify these two together. I'm done here. So again, to come up with my domains, I am going to think about my parent functions and what they look like. So hopefully you remember an original log graph looks like this. There's a vertical asymptote here at x equals 0, but this graph has been horizontally compressed by a half. That's not going to actually change my my domain, and then it's been shifted 1 unit to the right this time. So now what I've got is this horizontal, or the vertical asymptote being shifted here, and there's my resulting graph. So I can see that x belongs to the set of real numbers, and x has to be greater than 1, not equal to 1. It can't actually ever touch the asymptote. All right, so now the domain of g. G is an absolute value function, so hopefully we remember that an absolute value function looks like this. It's the V graph. And we've got here, this one, the k value hasn't been factored out. This is 3 bracket x plus 5/3. And so I do see that my graph has been shifted over to -5/3, and it's been horizontally compressed by a third. So it's going to look skinnier or narrower, and it's just shifted a little bit. But really, the domain of an absolute value function is always the set of real numbers. So I actually didn't even need to do a sketch there. Hopefully we just know that. It's kind of like a parabola, right? The domain is always the set of real numbers. All right, so now coming up with the domain of f minus g. And again, I'm looking for the overlap here. So where would these two graphs overlap, this red one and this red one over here? Well, it would only exist where the log graph exists. This whole section of the V that exists to the left of x equals 1 would just not be included in my new graph. There'd be nothing to subtract, right? Like if I put x equals 0 in here, it would be undefined. So I'd get undefined minus 5. I can't do undefined minus 5. It's still undefined. So x still has to be greater than 1. All right, and that's it for today's lesson. Enjoy your homework.